Good afternoon, everyone. I welcome everyone to this 1 week online National FDP. This program basically celebrates the anniversary of Mariam Mirza Khani, the only woman fields medalist till today. Now I just call upon C.H. Shamla from BSc Final Year FNBC, RBVR Women's College to deliver the prayer song. Sorry, to render the prayer song.
या कुन्देन्दु तुषारहार धवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेत पद्मासना या ब्रह्माच्युत शंकर प्रभृतिभिर्देवैः सदा पूजिता सा मां पातु सरस्वती भगवती निःशेष जाड्यापहा मातृदेवो भव पितृदेवो भव आचार्य देवो भव अतिथि देवो भव गुरुर्ब्रह्मा गुरुर्विष्णु गुरुर्देवो महेश्वरः गुरुर्साक्षात् परब्रह्म तस्मै श्री गुरवे नमः. Thank you, ma'am.
Thank you, Shamla, for such a beautiful prayer song. Now I just call upon Dr. J. Achita Devi, Madam, Principal, RBVR Women's College, Hyderabad, to say about the college.
Thank you, Shweta. Good afternoon, everyone. I welcome all the participants to 5 days faculty development program organized by Department of Mathematics, RBVR Women's College. Let me speak a few words about our college. Raja Bahadur Venkatrama Reddy Women's College was established in 1954 by Hyderabad Mahila Vidya Sangam, a non-profit educational society with a vision to empower women, especially those from rural areas, through quality education. The college is the second oldest women's college in the city of Hyderabad. The college owes its existence to the foresight of Sri Raja Bahadur Venkatrama Reddy, Kotwal of the erstwhile Hyderabad state, Sri Burkula Ramakrishna Rao Garu, the first Chief Minister of erstwhile Hyderabad state, Sri Madapati Hanumantrao Garu, former Mayor of Hyderabad and Chairman of the Legislative Council Andhra Pradesh, and Sri K.V. Rangareddy Garu, former Deputy Chief Minister of Andhra Pradesh, who were the pioneers in propagating women education in the state. This legacy of noble service to women education has been continued by successive managements comprising of judges, professors, and other people of eminence in the field of education. The college had the rare privilege of welcoming Pandit Jawaharlal Nehru, the first Prime Minister of India, who laid the foundation stone on 3rd January 1954. Dr. Sarvepalli Radhakrishnan, former President of India, who inaugurated the college building on 6th January 1955, and Srimati Indira Gandhi, former Prime Minister, who inaugurated the hostel building on 28th July 1965. The visit of Dr. APJ Abdul Kalam, former President of India, on 5th August 2005 to address the students on the eve of Golden Jubilee celebrations is yet another landmark in the history of college. Dr. C.H. Vidyasagar Rao Garu, Governor of Maharashtra, visited our college during the Diamond Jubilee celebrations. And our governor, Tamilisai Soundarajan, she awarded degrees to our college in recent convocation. The college is recognized by UGC under 2F and 12B. It is affiliated to Usmania University, conferred autonomous status by UGC since 1989, selected by UGC as a college with potential for excellence since 2010. It is accredited with A grade by National Assessment and Accreditation Council from 2007 to 2017 and was awarded B++ grade in 2018 in the changed accreditation procedure of NAC. I hope you will get loads of knowledge by attending this webinar. I congratulate Mrs. Sweta Srivastava and her team for organizing such a wonderful faculty development program. Thank you.
Thank you, madam. Now I request Professor Sudarshan Reddy, sir, Secretary cum Correspondent, RPVR Women's College, to address the gathering.
Good afternoon, everybody
Good afternoon, sir.
present in the webinar. I am happy to be part of this inaugural session of this 5-day faculty development program being organized by the Department of Mathematics and Statistics, not only for the teachers, but also for senior students, and even undergraduate students will get benefited from the outcome of the programs like this. In fact, programs like this will improve the skills and theoretical understanding of the themes, the theoretical understanding of the advanced as well as emerging areas of the mathematics. And I think the participants are drawn from across the country. It's a good development, and I congratulate Sweta and her team for organizing such programs every year. Even during the pandemic times, she conducted faculty development programs. I really appreciate the efforts made by her and her team. And this time round also, the resource persons are drawn from some of the best institutions in the country, such as Indian Statistical Institute, Ambedkar University, IIT Kharagpur, IIM Indore, Ishar Bhopal, and also other top institutions. I am very happy that the resource persons will speak during these 5 days on a very advanced and emerging areas of mathematics. And this is very interesting, and the 5-day deliberations will definitely make the participants learn some of the listen some of the best brains in the country and sharpen their skills, which will enable the faculty as well as senior students to pursue their research in the emerging areas of mathematics. I once again congratulate and appreciate the efforts of the mathematics department, and the management on behalf of the mathematics department and the institution welcomes all the participants and resource persons for this 5-day program. Thank you. Thank you very much.
Thank you, sir. And thank you for your continuous guidance for us, sir, so that we again, afterwards also, we will be conducting such kind of faculty development programs. I, Shweta Srivastava, Head Department of Mathematics and Statistics and coordinator of this National FDP. I just want to say about the faculty development program. The lectures are mostly related to basic branches of mathematics like algebra, analysis, number theory, differential equations, mathematical modeling, etc. One lecture is dedicated to the lives and works of Mariam Mirza Khani, which is delivered by Professor Nikita Agarwal Madam. And eminent speakers agreed to deliver lectures in this faculty development program. We have encouraged a youngster to deliver a lecture on a very famous woman mathematician, Emmy Noether's work. On the first day, Professor P. Suri sir gives a mysterious title, the Modular Mantis, to his no doubt very encouraging talk on group theory and modular forms. The next session, Professor S.D. Adhikari sir has consented to give a lecture on some classical results in combinatorics and combinatorial number theory. On the second day, the first session, that is the third session, a person with diverse interest, Professor Geeta Venkatraman Madam, will be delivering a lecture on some group theoretic problems. The fourth session, Professor T. Sukumar Kumar sir will be delivering a lecture in mathematical modeling. On the third day, first session, Professor Nikita Agarwal Madam gives a glimpse of life and works of Mariam Mirza Khani. The next session, Professor Pratima Panigrahi Madam will be delivering a lecture on combining graph theory and algebraic structures. On the fourth day, the first session, Professor Rukmini De Madam will be delivering a lecture on her current interest, minimal and maximal surfaces. The next session, Professor Hassan sir will be delivering a lecture about famous women of orbital mechanics. On the fifth day, Mr. Alap Hassan sir will be delivering a lecture on Noether's theorem. Professor Ekta Agarwal Madam will be delivering a lecture in analysis, the topic being improper integrals. This is all about the FDP, and now I just want to give a brief introduction of the Department of Mathematics and Statistics to all you. A quote by Abel Prize winner D. Sullivan. Sir, if you want truth, mathematics is the best place to start. The journey towards excellence is all about choosing the right path with a strong commitment and passion to excel in everything one does. Striving for excellence is a passion at the Department of Mathematics and Statistics, RBVR Women's College. We at the Department of Mathematics and Statistics, RBVR Reddy Women's College, with a passion to deliver quality and contemporary education in the area of mathematics and statistics, we are taking initiatives to bring in the contemporary teaching and research practices into our curriculum and pedagogy. Mathematics and statistics applications have a great utility and impact in the real life situations, and with the data sciences ruling the rule, their importance has further enhanced with applications like weather forecasts, health management, disaster management, financial analysis, and investment management, stock market application, fuzzy logic, and artificial intelligence systems, etc., which we have incorporated into our curriculum as projects, research, etc., which is bound to contribute to the academic world as well as to solve real-world problems. The Department of Mathematics and Statistics, in tune with its legacy and journey towards excellence, has taken quite a few initiatives and activities during last academic years, like introduction of certificate courses in mathematics and statistics, MOOCs courses as GE paper, collaborated with premier national institutes like IIG, NGRI, Just Smart Mandate, IIT Hyderabad for the student projects, summer internships, and research. We at the Department of Mathematics and Statistics believe in creating excellence by shaping and polishing the sharpest and finest minds towards synergizing their potential, skills, and energies to excel. Keeping the industry needs in view, we provide our students inputs in the form of guest lectures, workshops, research projects, use of softwares like Mathematica, Minitab, and Sage Math. mathematics day celebrations, academic clubs, etc., along with the regular teaching and training, which helps them by equipping them with requisite skills in their pursuit of excellence. Excellence without social responsibility is purposeless. We do understand the importance of social and moral responsibilities. We imbibe in our students to make them the ones with moral, social, and ethical values, and with the ones who can be treated not only for their skills and knowledge, but also their social concern. We do this with our association with School for Differently Abled Children, Manasa, under institution social responsibility, and we becoming the nodal department for certified voluntary work. I take this opportunity to promise that we will continue our pursuit of excellence and offer quite a few innovative certificate courses, curriculum, training programs, events, seminars, workshops, guest lectures, projects, softwares, etc., laced with social responsibility during the academic year and coming times. Let's journey towards excellence all the way take a new turn here. I sincerely welcome you all to attend all the sessions and benefit by the lectures. Thank you. I personally thank from the bottom of my heart Professor B. Suri sir, who has practically guided us for this faculty development program. Thank you. Good afternoon, Suri sir.
Good afternoon. Good afternoon to everybody.
Now I request Professor B. Suri sir to take over the session. Sorry sir, just a minute. Now I call upon C. Bhargavi to introduce today's speaker.
Thank you, ma'am. I'm audible?
Yes.
Good afternoon, sir. Good afternoon, everyone. I, C. Bhargavi, Assistant Professor from the Department of Mathematics and Statistics. I am feeling so honored to welcome our chief guest, Sir B. Suri. Sir has born on 21st August 1960, which coincides with the legendary birthdays of Cauchy, a French mathematician, and Usain Bolt, retired Jamaican runner. Sir likes reading English, Hindi, Tamil literature. Sir has completed his PhD under the supervision of Professor M.S. Raghunathan, FRS, on the topic algebraic groups and discontinuous subgroups. Sir has completed his MSc Mathematics from IIT Delhi in 1981 and BSc Honours from Mathematics from the University of Delhi in 1979. Presently, Sir is working as an Indian Statistical Institute, Bangalore Center. In 1999, Sir moved to the Bangalore Center of the Indian Statistical Institute, where the BMath Honours was to start, and Sir handled the first batch of the students, and the students honored the Sir by giving him a Best Teacher of the Millennium Card. Coming to his recognitions, in 2015, Sir elected for the National Academy of Science, and Sir is the national coordinator in charge of the Mathematics Olympiad program in India since 2016. He also served as the president of the Indian Mathematical Society for the year 2020-2021. For 3 years, Sir served as the secretary of the Ramanujan Mathematical Society, and he is also the member of the Board of Studies, Homi Bhabha National Institute, Christ University. He is also a mathematician member of the Mathematics Newsletter Committee at International Congress of Mathematics, Hyderabad 2010. Coming to the Sir's interest, Sir has various areas of research like linear algebraic groups, over global and local fields, division algorithm, character theory, and many more. Sir also visited various universities like University of Manchester, Imperial College London, and so on, many more. Sir published 3 books and a number of expository and educational articles for in summer, Sir being supervisor for 15 to 20 college students on their summer projects, arranging their stay in ISI Bangalore. Sir also has an interest in writing a poem, and Sir has written a poem describing the Ramanujan mathematics. Now, let us welcome the most experienced and well-versatile Sir B. Suri Garu to give his valuable inputs. Sir, we welcome you.
Thank you for this very long and unnecessary long introduction. Actually, I would have preferred a short one, which is lighter than this. You know, all these things don't make any sense much, you know, talking about what awards one wins and things like that. What one is interested in is what one would like to speak. First of all, congratulations to RBVRR College and also the principal, Dr. Achyuta Devi, and Professor Shweta Srivastav, and also Dr. Rama, whom I know very well, for organizing this 5-day meeting, mostly to honor Mariam Mirzakhani, you know, who is the only women's Fields medalist until now. And it's an honor to speak in this on this occasion. And maybe I should start sharing screen. Are you able to see now?
Yes, sir, we can see.
I think there is echo. I guess we have to make ourselves silent, except maybe I'll also take myself off the video so that there is no problem. Okay, so once again, it's a great honor and it's a pleasure and a privilege also to be the first speaker in this little meeting, which I think of as celebrating Mariam Mirzakhani's mathematics and her personality. And you will hear many other talks of different topics, including something about the work of Mirzakhani. My talk is going to be a general, easy talk, which I hope that everybody understands. I think there are students, they should be able to understand. So I sort of called it by a very catchy name. So the name doesn't make much sense until we go a little bit further. So let me just start. So first, I want to show this picture. I don't know whether anybody has seen this picture. See, when I give a talk, usually, of course, I would like to be present in front of people when I can see their expressions and I can ask them questions and they can reply. And depending on their answers, I go to the next sentence. But in this, unfortunately, we have to just go ahead with slides. I can't see people's faces also. So if anybody would like to answer on the chat also, you can tell me, what is this picture? Anybody has seen this? Looks like some different flowers. Somebody is doodling here. If you are lucky, you are done, and so on. It looks like some kind of some various surfaces here, pictures of surfaces here. So this is a doodle made by Mirzakhani. I just wanted to pass it on to how people work when they're relaxing also, they are doodling, and then their mathematics is going on. So just to show this. So this is one of the doodles she made before she got the Fields Medal. Okay, so I'll start with some very simple problem. First, I want to just mention in passing, at any point, if you cannot hear me or if you want me to repeat something, please let me know. I want to start with a very simple problem, which I won't talk about unless you're interested in it. This is an old high school problem of how a spider on a wall could travel along the walls to catch a fly on the opposite wall. This problem is probably familiar to most people. Just mention this, show this picture in passing. So this is the original problem. This is due to the great puzzlist Henry Ernest Dudney. The problem is that there is a room like this, which is a rectangular 30 feet by 12 feet by 12 feet. Here is a spider at the point A, in the middle of this wall, just 1 foot below the ceiling. And here is a fly at B, just 1 foot above the ground, above the floor. So the spider has to catch the fly. Fly is not moving. Spider has to move along the walls, of course, because it cannot fly. So what is the shortest path it takes? I guess this is something which is very well known. If somebody is, if it's still unknown to a lot of people, like or some people, I have a solution at the end here. But I would rather go ahead. This was just a prelude. So as I said, solution is at the end of this file, and I'll share this file at the end. But the problem that we are going to start looking at is of a praying mantis. You know what a praying mantis is? So this is on the, unlike this walls, here it is on the horizontal plane, and it is trying to catch a fruit fly. But this, our mantis is a very special type of mantis. It is what I call a lattice mantis. So it insists on traveling along only certain lattice points. Lattice points are points on the plane which have coordinates which are integers. Integer lattice points. So in the following figure, I've just mentioned the lattice points as centers of the squares. So the mantis always sits at the center of a square it occupies. And what does it do? How does it move? There is a fixed kind of move it makes. 4 types of moves. Movement of the mantis is restricted, as I said here. From a lattice point with coordinates u, v, it can move to one of these 4 points. U plus v, v, u minus v, v, u, v plus u, and u, v minus u. So see the following figure here. So here is our mantis. Let's say, if you can see the coordinates here. So this is the point 2, 3. The center of the square is the point 2, 3. So where all can it move? You know that the rule is that it can move to u plus v, v, etc. So it can move to this point, this point, this point, or this point. These are the 4 points. And of course, once it moves here, the same rule it follows, that it can keep on moving. Here the fly, which is the point, let's say, to begin with, the point 6, 4. So can this mantis catch this fruit fly? What do you think? This is sort of without any feedback. It is always very difficult to give a talk. Anyway, so a moment's thought will tell you that this can never catch this fly. How many? No, even if it takes several steps, several times. From here it can move to 4 places. From here it can move to 4 places. From each of them it can move to 4 places. But it can never reach here. Why is that? So let me go back once. What is the rule here? It can move from a point u, v to these points, one of these points. You notice one thing. Suppose it starts with the point 2, 3. Now 2, 3, 2 and 3 are co-prime integers. And this coprimality remains in this. If u and v are co-prime, u plus v and v are also co-prime. U minus v and v are also co-prime. In other words, this mantis, wherever it moves, the coordinates have to be co-prime coordinates. So it can never go to 6, 4. Okay. So it's clear that the 4 points to which the mantis can travel can be represented now in terms of matrices. It's a convenient way of doing it. So let's call this matrix 2 by 2 matrix 1, 1, 0, 1. And think of this point u, v as a column. Then you have this matrix multiplication x dot p, which is this, and you can see it is u plus v, v. So there is a convenient way of representing the points that the mantis moves from here. So what are the 4 points? The 4 points are this x dot p and x inverse dot p, y dot p and y inverse dot p. What is y? Y is this one, 1, 0, 1, 1. Remember, x was the upper triangular, 1, 1, 0, 1. And the inverse of x, this matrix is 1, minus 1, 0, 1, and inverse of y is this. So these are the 4 points that the mantis can move to from u, v. So having established how the 4 points arise in each step, it's clear that the points can be reached. What are the points which can be reached after a finite number of steps? That means it either goes x dot or y dot or x inverse dot or y inverse dot at each step. So it's going to be a word where the symbols, your letters are x, y, and x inverse, y inverse. Your alphabet consists of these 4 letters and you have a word in that. So you take any word in this language and apply it to your point where the mantis is sitting, you get the possible new points. All the words you consider of finite length. These are all the points that mantis can move to from u, v. So as I said, U comma V, I mentioned that U comma V, they have no, they are co-prime, then wherever it moves to is also co-prime, but we can say more than that. If U comma V have a particular number as a GCD, the GCD does not change. U plus V comma V also has the same GCD. U comma U minus V, so they also have the same GCDs. Greatest common divisor. So greatest common divisor of the points don't change in this mode at each step. So the problem actually becomes interesting when we want to know whether starting from point, can we reach every point to the same GCD? Can we reach every point x comma y where the GCD of x and y are also equal to GCD of u and v? The GCD of x, y should be equal to GCD of u, v for it to be, this is a necessary condition as we have seen. But does it move to every point? That's the question. So of course I have to mention here one small thing. If you notice, suppose the mantis were sitting at this origin 0, 0, where can it move to? See, from the rules, it cannot move anywhere. It just has to sit there. 0 plus 0, 0 minus 0. So it's just going to be here. So the caveat is it should not be at this point. Then it cannot reach anywhere. So let's say it starts with any u comma v, where u comma v is not 0, 0. So firstly, natural question that arises. So starting from a point, after some finitely many maneuvers like this, does it come back to the same point? I mean, not just retracing the path, but some other path, maybe does it come back? Does it return to the same point? So this is why it's convenient to pose the problem in terms of these matrices. So this means, is there a word in terms of this xy, x inverse, y inverse, finite expression of products of xy, x inverse, y inverse, which is identity, and which is not the trivial representation. X times x inverse identity. I don't mean that. So have non-trivial word is there or not? That is the question. Any question? Anybody? Mm-hmm. Okay, but a little bit of observation, a little bit of experimentation will tell you that y x inverse y, when you apply 4 times, you will return to the same point. You just multiply out of the matrices and see y x inverse y. Okay. Similarly, when you apply y inverse x 3 times, it's minus identity. So when you apply it 6 times, it's identity. That means what? When you go along the word y inverse x 6 times, you return to the same point wherever we are starting from. So there are non-trivial words like this which are identity. So at this point, I should tell you that the main character of her story, the heroine of her story, has already entered. She is called the modular group. So the modular group SL2Z means the 2 by 2 integer matrices. Z is for integers of determinant 1. Okay, so sometimes I'll call this as a modular group. Sometimes I'll call something which is twice as big as this, namely integer matrices of determinant plus or minus 1 as modular group, or half of this as modular group. Mean you divide out this group by the matrices plus or minus identity. You identify the identity and minus identity matrices. It's called PSL2Z. So that's not so serious. So this matrix, this group of matrices, 2 by 2 integer matrices of determinant 1, we are calling as a modular group. That's the origin of the word modular. We'll see why that comes. Every matrix is expressible as a word in this. See these matrices of determinant 1, 1, 1, 0, 1, etc. 1, 0, 1, 1. The question is every matrix with integer entries, determinant 1, is it expressible as a word, a finite word in this? So indeed a very interesting question. Why is it important for us? So before I show, let's show whether it's true or not, or to show that it is actually true. Let's see how important. Sorry? Any questions? Feel free to ask. Okay. So let's see how important this information is for us. You remember, one of the obvious questions was starting from a point u comma v, can we reach any other point x comma y which has the same GCD? Every other point. I'm saying this information that SL2Z, every matrix is expressible in these 4, will answer that question. Why? Because if u, v, and st are lattice point with the same GCD, we can very easily show that there is a matrix integer matrix determinant 1, which takes this point to this point. We are sure that we can take any u comma v to s comma t, they have same GCD, by some matrix of determinant 1, integer matrix. But of course, we would like to know whether we are able to reach by the Mantis steps. That would be true provided every matrix is expressible in terms of x, y, and x inverse, y inverse. So let me just first prove this, that every point u comma v goes to s comma t. So to do this, if you take out the GCD of the two pairs, you can write capital U, capital V, capital S, capital T. We have taken out the GCD, which is a number D. So this equation is same as this equation without the D, capitals here. So you want a matrix satisfying this, and I'll explicitly give you this matrix. What does it depend on? It depends on the following fact. When U and V are co-prime integers, now they are co-prime integers, we have taken out the GCD, then there is a linear relation between them, AU plus BV equal to 1. Similarly, capital S and capital T, there is a linear relation like that. You know that the Euclid's division algorithm will tell you that GCD is a linear combination of this two, integer linear combination. Using that, you can explicitly produce this matrix G. You can check that this is determinant 1 integer matrix and takes matrix calculation. Okay. So what we have said is that any 2 points, the same GCDs are taken to each other by a matrix in SL2Z. Now the proof that every matrix is expressible as a word in the 4 matrices, I'm telling you that that's also nothing more than the application of usual division algorithm, Euclid's division algorithm. I'll just very briefly tell you and before you go further. So take a matrix in SL2Z, you want to say it's expressible in terms of this. Means what? Suppose you apply to that matrix left or right multiply by something like this, and keep on left and right multiplication, it reduces to the identity matrix. That's what it means to say this is expressible as a word in there. So what happens when you multiply by powers of x and y? Of course, I said powers of x and y will lead to one of these matrices, but minus of the identity matrix is expressible. We already seen this. So everything will be expressible. Okay, so we have to show that left and right multiplication by powers of x and y to any matrix leads to one of these two matrices. Since it is very simple and explicit, I'll show it to you here. So start with any matrix G, which is matrix determinant 1. So now look at x to the power r. Remember, x is the matrix 1, 1, 0, 1. X to the power r happens to be 1 r 0, 1. You can calculate that. So when you calculate this product, it turns out to be this. You notice this now, a plus rc, which means if c is not 0, we can divide a by c and take r to be the quotient and a plus rc will be the remainder. In other words, you are replacing a by the remainder now of a division by c. So multiplication by power of x manages to reduce a to the remainder of division of a by c. Similarly, now we can divide c by dividing by this. Similarly, one can then by left multiplication by some y power r, which means 1011 power r. This is 1101, this is 1011. One can reduce c mod a as before, and then you'll keep on reducing. The numbers are integers are reducing in size. So ultimately, they have to become, one of them has to become 0, either this or this. Either a or c, after a finite number of steps, multiplying by x power, y power on the left side, either this becomes 0 or this becomes 0, a or c. So g becomes either something like this. You see, if this becomes 0, I'm claiming that this has to be plus or minus 1. Why? Because if this becomes 0, determinant is 1. So the 0 minus something is 1. So the product of two things must be plus minus 1. So both are the plus minus 1s. So now reduce any matrix to this form by multiplying on the left by a power of x or a power of y, those two matrices. Or if this is 0, then it becomes like this. So in both cases, I just want to say, I can just easily do this simple calculation. It's in front of you. So it's very explicit and simple to say that every element in SL2Z is a product of these two matrices, x and y, and their inverses. They may repeat x, y, x square, y, x power minus 3, y inverse. It could come like that. Any word like that. Okay, so that tells you that any point of the same GCDs can be taken to each other by means of our maneuver. Which maneuver? The one which is allowed for the mantis. Because those maneuvers will generate a whole SL2Z. Okay, let's think of a variation of the above problem where it cannot move backwards. Okay, it can move from UV to only to U plus VV or U to UU plus V. So it's going either to the right or upwards. Okay, from a point, you can move only to the right or upwards. In other words, only positive powers of x and y are allowed. Starting from a point where the GCD of the two coordinates is equal to 1 and both are positive, let's just say it's positive, because after some time, when you keep on moving right or up, the point becomes positive. So let's start with a positive point. Mantis can reach a point PQ, coordinates PQ, which are primes. Do you see why? Allowing these two kinds of moves, it can always reach a point with coordinates which are prime numbers. This uses some very, very well-known theorem. If you can recall, if you can see what theorem it is, it's a so-called Dirichlet's theorems on primes in arithmetic progressions. When U and V are relatively prime, then you can keep on adding to V multiples of U, V plus U, V plus 2U, V plus 3U, etc. And we are going to hit primes infinitely many times. That's what Dirichlet's theorem will tell you. So because of that, Dirichlet's theorem will tell you U plus, there is a prime of the form U plus NV, which means when you are moving horizontally, you can hit a prime with the first coordinate a prime. Horizontally, U comma V go to U plus V comma V, U plus 2V comma V, etc. Ultimately, U plus NV comma V, which is a prime. U plus NV is a prime. Similarly, now that you have U plus NV, now you can start moving vertically. So your new U is U plus NV. Now change V mod this. Having reached PV, we may choose a prime Q of the form P plus MV. So you are moving on the vertical direction. V is changing to like that. I should have said V plus MP. There is a misprint here. V plus MP. Vertical direction you are moving. Anyway, so primes can be reached. Here is a more difficult question. There is some noise coming. So my place also some construction work is going on. Okay. More difficult questions. Starting from any pair of co-prime positive integers, can it always reach a point of the form R square, T square? Both squares. This is slightly more involved, but again, elementary number theory, slightly higher level, namely, we will have to use something called the quadratic reciprocity law of Gauss. Okay. So I'll just briefly mention this here before going further, because I want to point out a couple of things also before going further. For instance, start from the point 2, 3. How do you reach a prime two squares? Suppose I just keep on moving along horizontal direction, which means what? 2, 3 goes to 2 plus 3, 3, which means 5, 3. It goes to 8, 3, goes to 11, 3. You can never reach first coordinate of square. When you go horizontally, you can keep on going horizontally. You can never reach a number whose first coordinate is a square. Can you see why? Because the number is going to be of the form 3 plus 2k. 3 plus 2k. Sorry, 2 plus 3k. Horizontally we are going. 2 plus 3k. 2 plus 3k can never be a square. See, when you divide a number by 3, square will have remainder either 0 or 1. Okay, so when you go along the horizontal direction, just keep on going. You will never hit a point with the first coordinate is a square. So you'll know that you have to mix up things. So here is one way of doing it. As I mentioned, you can never reach a point by just going horizontally. So we can go something like this: 2, 3, 2, 5, 2, 7, then go to 9, 7, and 9, 16. So this is a particular example, of course. So are we guaranteed that we can always reach a point with both coordinates perfect squares? So here is an argument which I'll sort of quickly go through here, but just don't want to spend much time on this because I want to go to other applications. So remember, we are starting at the point A comma B where A and B are relatively prime. We want to reach from A comma B some point where both coordinates are perfect squares. And we are only allowed to move right or top. It means A plus B comma B or A comma A plus B. So A and B are relatively prime. So at least one of them is odd. Both can't be even. So let's say B is odd. Let P be a prime that is congruent to A modulo B. This is what I mentioned. The Dirichlet's theorem and primes and progressions tells you that whenever you have A and B relatively prime numbers, co-prime numbers, then can always go on the arithmetic progression, multiples of B and A added, that always contains infinitely many primes. So we can find one prime at least like this. And simultaneously, you can assume that the prime is of the form 4k plus 3. Okay, I should say why that is so. Such a prime exists by not only by Dirichlet's theorem, which is of course a very deep theorem, but also Chinese remainder theorem. You can always choose something which is of the form 4k plus 3 and choose a prime which is in the progression A plus NB, and then you can choose a new prime which is congruent to both of them. Anyway, so simultaneously you can choose a prime which is in this of the form A plus NB and it is of the form 4k plus 3. So in a finite number of moves from AB you can reach PB because A plus NB is P. Okay, now I'll tell you why this 3 mod 4 comes in. Similarly, you choose a prime Q that is congruent to B mod this P. You're moving this one now. So you move, first you move the first coordinate, now you're moving second coordinate. So you can reach prime PQ. Now the special thing about PQ is that both are of the form 4k plus 3. There are two prime numbers of the form 4k plus 3. Here is where something called Gauss quadratic reciprocity law comes. It's famous quadratic reciprocity law. It says that we have two prime numbers, both of the form 4k plus 3. Either P is square. It's okay. So if you have two prime numbers of the form 4k plus 3, we can say quadratic reciprocity law will imply that either one of them is a square mod the other, only one of them is a square mod the other, not both, because both are 4k plus 3 type. Okay, if you don't know reciprocity, people who have not seen reciprocity, you can just take this as a consequence of reciprocity. And using that, we can easily complete this proof. I don't go through this slides here. Okay, it's here. So it's nice to see that you can reach points with both coordinate squares. And it does need some slightly non-trivial number theory. Okay, now I just want to sort of come back to the center in some sense and coming out of the problems that I started with, lattice mantis sitting on the lattice and things like that, because that is just to introduce our heroine of the story, so to say. So I'll start with this comment. The great mathematician physicist Hermann Weyl referred to the group JLN of all invertible matrices as, he called it the her all-embracing majesty. So everything is emanating out of her. So this is a very famous phrase he used for the her all-embracing majesty for this group of invertible n by n matrices. So in that vein, we are talking about the 2 by 2 integer matrices, determinant 1. So sort of they are subgroups here, but they are subgroups with integer entries. Here you can have any complex number, real entries, and so on. So integer entries. So let me call this as a discrete cousin. You can call it as English word discrete, or the discrete is a mathematics word because of integers. Okay. In the remaining time, we want to draw attention to how this modular group SL2Z, that is 2 by 2 integer matrix of determinant 1, plays a role in many situations. Okay. I talked about one elementary problem where it played a role, namely the mantis movement. But I'll talk about other applications. Some of them I'll just mention the applications without proofs, just striking statements. It will tell you how ubiquitous it is. Everywhere it is there, SL2Z, the modular group. So first application of modular group, I think Dr. Uma would tell you that if she knows me, that I always like to lighten the atmosphere a bit, either write a poem or maybe make a joke in between so that you wake up. The first application of modular group is, oh, sorry. So this is, I think this is called a modular kitchen. I didn't mean that. Okay, so I hope you're woken up because of that. So I'm not going to be talking about modular kitchens. So the group, modular group. So let me just mention a few statements in mathematics, striking statements. Common thread running through all of them is the role of modular group. Since there are innumerable, so many of them, I'll just mention a few statements and then perhaps talk about how the proof goes for one or two of them, or one of them. So here is the famous equation. This is some people who are interested in history of mathematics and our Indian role in it and so on would have seen this and may remember this. What is this expression? This is called a continued fraction. This means the way you are written it here is e power minus 2 pi by 5 divided by something. What is that something? It is 1 plus something. What is the something? It is again e power minus 2 pi by 1 plus this. So this is shorthand way of writing. Otherwise, it becomes very difficult to write this whole expression, finite expression. A1 plus 1 by, A2 plus 1 by, A3 plus 1 by, like that. This is infinite, it never stops. This funny number, infinite expression, is equal to this. So some of you would have seen it and you will be wanting to say, yes, I know this. This continued fraction appeared in Ramanujan's very first letter to Hardy, written on January 16, 1913. So can you imagine the feeling that Hardy must have got from letter from this unknown Indian. So looking at this formula, much later Hardy said this. They defeated me completely. I had never seen anything in the least like them before. A single look at them is enough to show that they could only be written down by a mathematician of the highest class. They must be true, because if they're not true, no one would have had the imagination to invent them. So if you want to write you are crazy and want to write a very bizarre formula, what can you should have enough imagination to write a very bizarre formula. So this is so bizarre that it must be true. We cannot have the imagination to invent such a bizarre formula. If you invent a formula, it will be easy to find out, right or wrong. Anyway, this continued fraction can be proved using the so-called Ramanujan identities. These are related to the so-called theory of partitions, to which, as we know, Ramanujan made fundamental contributions. So Ramanujan's work also has to do with modular group. So I want to mention theory of partitions. Partitions is what? Simple. The definition of partitions of number n, natural number n, is how many ways can you write the number as sum of smaller numbers. Okay. Partitions of 4 are 4 itself, or 3 plus 1, or 2 plus 2, or 2 plus 1 plus 1, or 1 plus 1 plus 1 plus 1. So these are partitions. This is a very mysterious function, partition function. For example, what is the exact number of partitions? Here, well, if you are interested in exact formulae, here is the formula. And it's not important what the, precisely what is the expression here, but notice that it is very, very, very surprising, amazing, because it involves things like 24th root of unity and things like that. Number of partitions have to do something with 24th root of unity and so on. Now, this is bizarre, but okay, so I'll mention something about it later. So this is one place where a model of group SL2Z plays a role. Here is another place. This is a very familiar one where you know that every prime number of the form 4k plus 1, which Fermat wrote, is the sum of two squares, can be expressed as sum of two squares. Okay, Fermat's theorem that every prime number of form 4k plus 1 is a sum of two squares of integers. So this can be proved different ways, but of course there is a theory of quadratic forms. When quadratic form of this form, quadratic form simply means a degree 2 expression in x and y, two variables, homogeneous expression. Okay, and this quadratic form has integer coefficients p and q and things like that. So this takes the same values as this, and because of that, the fact that these two take the same values comes from the role of modular group. Okay, so obviously from there it turns out that every prime number is of the form 4k plus 1, because this takes a value prime number, right? You can take y to be 0 here. Values taken by this quadratic form, x equal to 1, y equal to 0, is the value p. So p is taken as a value here. So p must be taken as a value here. So it's another proof of Fermat's result. And it gives many more things like this. So this is about equivalence of quadratic forms. They are also modular group. And here is a very curious looking thing. Look at the number e to the power pi root 163. If you calculate that, okay, it's a very complex, very big expression. Of course, it's not an integer, but what turns out is that up to 13 decimal places, it is 9999 like that. Okay, it will not be an integer. It will be irrational, but it is very close to an integer. So the fact that this is very close to an integer comes from the role of modular group. This number 163 very special. This is a very biggest number of this type. This kind of result you want to get, 163 is the biggest one. I will not go more into it. This comes from what is called theory of complex multiplication. Okay, now it's something more familiar. Sum of powers of divisors. So let's look at the natural number n and sum of the rth powers of divisors of n. This is a function which counts what? Sum of the rth powers of divisors. So sum of divisors, sum of squares of divisors, sum of cubes of divisors, etc. Sigma n, sigma 2n, sigma 3n, etc. Okay. So these are nice functions which you would like to know. For example, how many ways can you write? Or what is the sum? So here some very unusual looking relations. This relation you can explain it to a school kid in middle school. Sigma 7n means sum of the divisors, 7th powers of divisors of n. For any n, some of the 7th powers of divisors of n, some of the 3rd powers of divisors of n are connected by this. Similarly, some of the 9th powers of divisors, some of the 5th powers of divisors are connected by this. 3 is also occurring here. So just by looking at the number of divisors, we cannot guess this. These actually drop out of some theories. So what the theory is that again modular group plays a role. I'll come to that now. So see some very familiar looking or very elementary looking number theoretic counting is made possible by our group. So let's look at, suppose Rkn is the number of ways a positive integer can be expressed as sum of k squares. No? Number of ways of writing n as a sum of k squares. For example, number of ways of writing n as a sum of 2 squares is R2n. Number of ways of writing a natural number n as a sum of 4 squares of integers R4n. All these are studied. Any question? So we have formulae of this kind, explicit formulae. Now, see, in what happens often in mathematics is, suppose you want to say every number, suppose you want to say is expressible, every natural number is expressible as sum of 4 squares of integers. The way often it goes is that you look at the function which counts the number of ways that you can write n as a sum of 4 squares. You have to show that the number is non-zero to say it's expressible, but you can't directly say it is non-zero. You should say that it grows at least as big as this. So funnily enough, to say something is non-zero or positive, you show that it is at least as big as this. Because if you want to study the function, you can use other techniques to study the function, how big it grows. Because it grows big enough, it is non-zero. We really like to know if it's non-zero or not. So this is a funny aspect of mathematics. Often it happens. You cannot say something is non-zero or positive unless you say it is at least as big as this. So for example, these functions, number of ways of writing sum of n as sum of 8 squares is given by these explicit things. Okay, one more thing I'll jump to, which is something to do with Mirzakhani's work. Suppose one considers continued fraction expansions of rational numbers. Okay, so suppose 31 by 13, look at. Here is a continued fraction. What does this mean? That means 31 by 13 equals 2 plus 1 by 2 plus 1 by 1 plus 1 by 2. That's what this is. But suppose you allow negative numbers also, then here is a shorter expression. 2 plus 1 by 3 minus 1 by 3 plus 1 by 2, etc. Okay, second one is obtained by choosing a nearest integer at each step. Instead of, how do you get a continued fraction? You just take the remainder each time and take this integer which is just smaller than that. That's how we get continued fraction expansion for a rational number. So base finite continued fraction. Okay, so if you calculate 2 plus 1 by, so take a 31 by 13 is 2 point something. So it is 2 plus something. What is the remainder? 5 by 13, right? So 5 by 13 you want to write as 1 by 13 by 5. 13 by 5 is 2 plus something. That's why 2 here, like that. So finally it will stop because the numbers are decreasing. For a rational number, there is a finite continued fraction always. And if you allow negative numbers, we have possibly shorter ones also. Is it true that a continued fraction expansion of rational number each obtained by choosing nearest integer at each step is the shortest one? This is it's like classical problem. Okay. Is it also true? Second question. Take the continued fraction of a rational number, the shortest one, if and only if all these integers are of mod bigger than or equal to 2, and from this stage onward, B1 onwards, and B1, B2, Bn does not have any substring of this form. 2 minus 3, 3 minus 3, 3 minus 3. Okay, that is the question. So this, how can it come up with this question? We cannot come up with these questions. It's not natural. It comes because you are trying to solve the problem some way, and these conditions drop out. I'll come to that. This I'll talk about a little bit. The answer to both questions turn out to be affirmative actually. So this is something very elementary, but the only way to tackle it is using some higher mathematics. The common thread and the rather different statements is our heroine, the modular group, as I mentioned. So as I said, our modular group we can think of as, depending on the situation, 2 by 2 integer matrix of determinant plus minus 1, or just determinant 1, or the quotient of this group by the plus minus analytic. So this is like half of this matrix, half of this group. So one of these you'll see. For example, I mentioned here is a formula for partitions. I mentioned there is an explicit formula due to Radha marker, this one, where it involves some 24 roots and so on. No, exact formula, of course, is due to Radha marker, but it comes from an asymptotic formula, which is due to Hardy and Ramanujan. So, exact formula for Pn written down by Radha marker is essentially follows from the so-called Dedekind eta function. Okay, I'll recall this. So, the word modular form we'll come across now soon, but I just already called it a modular form. When we study some number theoretic sequences, suppose like you want to study the function sigma of n, sum of divisors of n, or you want to study the function number of ways of writing n as a sum of 4 squares, R4n. All these, the way to study them is put a generating function. That is, look at summation R4n z per n. That's a function in z whose coefficients are your R4n for different n's. You study the sequence by this generating function. So these generating functions often tend to have remarkable properties. How they transform when z is variable changes from z to something else, linear change. So this is, and the change, when you change z by something like az plus b by cz plus d, where ABCD is 2 by 2 matrix for determinant 1. That is how the modular group comes in. So the so-called modular forms, okay, just to say nowadays, this is the thing to say, you say the role of modular forms, that is functions which transform under transformation by the modular group. When you change the variable z to something like az plus b by cz plus d, where ABCD is a 2 by 2 matrix of determinant 1, those functions are called modular forms. Now they say that there are 5 basic operations in mathematics. The ones addition, subtraction, multiplication, division, and modular forms. This is considered as basic as that. It looks strange to us, but that is how it is. That's how important it is now. So roughly, modular form, as I said, is a nice kind of function defined on the z belonging to the upper half plane. I will not go into y upper half plane. Complex plane you can think of. Then f of az plus b by cz plus d. Change the variable to this, then it is just the f of z except one factor like this. Cz plus d power something. Where ABCD varies over our group of integer matrices determinant 1. So for example, look at the generating function from partitions. This is the one. You can write this. Here is 1 by 1 minus q. You can expand as a geometric series. 1 by 1 minus q square expand as a geometric series. Multiply out all the infinitely many geometric series and gather together the coefficient of q power n. It will turn out to be number of ways of writing n as sum of smaller numbers. So that is why this is a generating function. The elementary to see. So-called eta function is defined like this. Dedekind eta function. defined by this infinite product in terms of variable z. You see there is a relation to this, because you can see that is because of this 1 minus q power n. If you think of q as e power 2 pi I z, then there is a relation. Eta z is this number. Pn is the number of partitions we are interested in. And we have introduced this new function called eta of z. The reason we have done it, eta of z happens to be a nice function, the so-called modular form. So in fact, it has this relation. Change z to minus 1 by z, value becomes this. Okay, and you see eta is intimately related to partition function. So if you know something about eta, you should be able to deduce something about Pn, and that's what happens. Using the transformation above and 1 for eta of z plus 1, one gets the transformation formula for any eta of az plus b by cz plus d, because SL2z, as we said, is generated by those two x and y, right? Similarly, generated by, this is your z going to z plus 1 is like your x matrix. And z going to minus 1 over z is also in terms of x and y. So these two will generate whole SL2z. Every matrix can be written in terms of these two transformations. Z going to minus 1 over z, z going to z plus 1. Will generate all z going to az plus b by cz plus d. The same proof that I gave in the beginning, actually. Anyway, so this group can be generated by these two matrices. Remember, az plus b by cz plus d, where abcd is this, means minus 1 over z. Minus 1 over z. Okay, the function eta of z plus 1, yeah. So using that, you can show that eta satisfies this kind of transformation law. Variable is changed to new variable like this. Then there is, in terms of the original value, there are some sums called Dedekind sums which come. That's why it's called Dedekind eta function. This can be explicitly written down, these sums, but I'm not doing it. So using this expression quite easily, this is the one which gives expression. Explicit formula for the partitions of n comes out of this, just drops out of this. So if anybody who's interested in it can look at this Theory of Partitions book by George Andrews, and we'll tell you how this implies the explicit formula for P of n. Okay, so that is one thing. Now coming back to this continued fractions and geodesics and hyperbolic geometry. So you see, now we're going to relate something as concrete as continued fraction for rational numbers to some geometry. So actually this, as I mentioned, is related quite a bit with work of Mirzakhani. I can't tell you directly because it's a complicated relation. But let's come back to continued fraction. You said 31 by 13 has this continued fraction, and there's also this continued fraction, which is shorter. What happens is, what is the relation associated to any continued fraction? It turns out that one has a path in a graph. We want to form a graph called a fairy graph. So even if you, I'll show you this, of course, but point is, I'm saying continued fraction is a finite expression like this. 2 plus 1 by 2 plus 1 by 1 plus 1 by 2, whatever. Associated to that, I'm going to give a geometric picture. It will be a path in some graph between some point and another point. And if you have another continued fraction, it will give another path. If you give another continued fraction for the same number, it will give another path. The shortest continued fraction will be given by the shortest path. So that is the relation it's going to be. So facts about continued fractions, which is what is a very basic questions, can be solved by going to this more complicated situation of geometry. And so I'll say, what is the picture here? What is this fairy graph and what is this path and all that? So just to mention very quickly that for any integer a, look at this transformation. So this is a particular transformation, z going to az plus 1 by z. That is a plus 1 by z. This is it. Okay. So when you think of as a plus 1 by z, I can think of infinity going to a, 1 by infinity is 0. Think of it like that. So this is acting on all the points, including 0 and infinity also. And so this transformation is nothing new to us. It is in terms of our z going to z plus 1 and z going to 1 by z. This is applying a times this and then applying once this. So we can say that no, lo and behold, this infinity, where does it go to by SIN? It will exactly go to this continued fraction. That is the relation between these transformations and continued fraction. Okay, because you apply it once and see SAN of infinity is going to be AN. Take SAN minus 1 of AN, what happens? You apply it here and see, and it will turn out to be AN minus 1 plus 1 by N. will keep on going like this. So this is just this. So in other words, you can view the continued fraction as transformations on the upper half plane. Where is infinity taken? Infinity is the point at infinity. So vertically top. So I'll show a picture for that. So this SAs will generate SL2Z, GL2Z. GL2Z meaning determinant plus or minus 1. So it is double our SL2Z. So I'm not being very, it's almost correct. So I'm asking GL2Z. So there is a bijective correspondence between finite continued fractions and words in T and S. So what is a fairy graph? I said there is a graph and the shortest path between points correspond to continued fractions and so on. So what is a fairy graph? It is just vertices are rational numbers, and this is joined to this by a semicircle if this relation is there. This relation is like determinant is plus minus 1, that relation. So the upper half plane has a kind of metric. It's called a hyperbolic metric. Okay, just like your sphere has a different metric, plane has a different metric, upper half plane has a different negative curvature metric called hyperbolic metric. Metric means distance, the notion of distance between 2 points. So when you have notion of distance between 2 points, you can talk about what is the shortest path between 2 points. Shortest path between 2 points in that metric, in that new notion of distance. So what happens is in the upper half plane with this metric, the shortest path between 2 points, from this point to this point, suppose this point is here, it is like this. So it's a semicircle perpendicular to the x-axis and passing through both these points. Or if they're both on the same vertical line, that's also geodesic. Geodesic means shortest path. So the shortest paths are of these two kinds. Vertical lines or semicircles perpendicular to the x-axis. We have bijection between finite continued fractions and finite paths from infinity in the fairy graph. So here is one picture. Okay, here these are all geodesics. They are all shortest paths. Vertical lines are also shortest paths. So all these points sort of going to this point I infinity. So there are various paths from infinity to here, and as we know that matrix SA will take infinity to the point A. Okay. So I'm just showing more and more of these paths. Shortest paths like this from infinity, like this. So the question whether the nearest integer continued fraction of a rational number is a shortest continued fraction, shortest one in length, is equivalent to the question as to whether the corresponding path is the shortest. It means path is what is called a geodesic. Geodesic is another word for shortest path. In fact, it's not just for fun you're doing this interpretation. This is the interpretation used to solve that question of continued fractions. Recognition of paths that which are geodesics leads to a statement of the continued fraction made earlier, which is this bizarre looking condition. I said such conditions you cannot guess, right? Which is the shortest one? This is shortest one if and only if this condition holds. This does not contain substring of this form. Experimentally to see this is also difficult, but this drops out of the geometric proof. What is the shortest path? From there it comes out. Okay, so if you like, continued fractions is a very old subject, but modern subject like hyperbolic geometry, it's also old subject in some sense, but modern methods will give proofs of such thing. This is not old hat. So I want to mention Zaremba's conjecture. I have about 4 minutes, I think. So someone should not think that continued fraction is old hat. So here is an open problem, still open. So there is a positive n for which every f positive arises the denominator of a rational number whose continued fractions have all these terms less than or equal to n. So there is a bound n like this. So it takes a little while to understand this conjecture, but this conjecture is, a lot of things are known due to modern methods by various active mathematicians now who have collaborated with Mirzakhani also. There are people like that. So it's not unrelated to her work. She works on Teichmuller spaces, but this is about, again, hyperbolic geometry. So Zaremba's conjecture, okay, so I don't want to say anything more about this, just this is still an open conjecture. So from the analytic or algebraic properties, one can often draw number theoretic conclusions. So I want to mention quickly this, coming back to the sum of rth powers of devices and number of ways of writing n as sum of k squares or kn. So what are the generating functions for this? Well, and how do they transform with respect to our group SL2Z? Here is a very nice function, theta function it's called. Look at this function, it is an infinite series e power I pi n square z. What happens when I take kth power of this series? So you have e power I pi n1 square z summation, e power I pi n2 square z, like that, k times you are putting them. So when you gather together and put something times e power I pi, I don't know, mz, then what is that m? M will be sum of k squares, n1 square plus n2 square plus nk square. When you gather together, theta set power k, just take the same series k times, multiply out, gather together, what is the coefficient of e power I pi something, nz, that will be a number of ways of writing n as n1 square plus n2 square plus nk square. So you see, you got a nice function which generates the function that we want to study, Rk of n. What we want to study is the elementary function Rk of n, but we have produced a series like this called theta series. This theta series transform very nicely with respect to a modular group. So because of using that, you have such relations I mentioned here. I said we shall return to this later, but I may not return to this later. So using this series, how it transforms, you get these equalities. So finally end with this part. Look at this series. Here is a double series. C and D are both varying over integers. This is 1 by Cz plus D power 2k. So function of one variable z, where C and D are both varying over integers. Of course, C and D are not both 0. That is why this sigma dash I put 2k. And where does it converge? Wherever k is bigger than or equal to, it converges. So does it show that actually this converges for whenever alpha is bigger than 2? It is exactly same as saying the harmonic series converges sigma 1 by n power alpha converges for alpha bigger than 1. From there it comes. Anyway, so when you look at this series, the function that that defines, I'll just take another 2 minutes. You see when z changes to z plus 1, it is the same series. Because we are going through Cz plus D, C and D varying over integers. So when you take instead of z, z plus 1, it is the same series. So g of z equal to g of z plus 1. You know such functions are periodic functions. So we have Fourier expansion. So such things are used. Using that, you have an expansion in terms of e power 2 pi I z. That's what I meant by Fourier expansion. And you have, these are the coefficient here. When you actually calculate, these are the coefficients, and this is a zeroth coefficient. Constant term, which is given in terms of value of what is called this function series. It is called a Riemann zeta function, famous summation 1 by n power. So values at 2k are given as constant terms here. And these are functions, sum of 2k minus 1 powers or divisors come as coefficient of this. Because of this transformation property, it's a Fourier series. This is a Fourier series. Anyway, so I told you how it follows. This is very easy, elementary. I don't go through it. You can look at it. That's how this follows. Okay. The formula that I mentioned here follows very easily by looking at an expansion of pi cot pi z and differentiating and so on. So this is very easy to prove, elementary to prove. In college, you can prove it. Okay, so I mentioned this related to GKZ is EKZ, which is just normalized here. I just divided by this so that the constant term becomes 1. Okay. So there are examples of modular forms. So why these relations come is something like this. So very shortly, I'll just say modular forms form vector spaces. Modular forms are what? Functions which satisfy some transformation property with respect to the modular group. So each of them have a given weight. Weight is coming like this: f of az plus b by cz plus d is cz plus d power k times fz. K is called the weight. So what happens in each weight? There is a finite dimensional vector space they form. So for example, suppose there is a one-dimensional vector space, we have two candidates for that element of that. You know that there must be multiples of each other because of one-dimensional space. Because of such simple reasons, relations like this come. You have some dimensional space, a two-dimensional space, you have three candidates elements there. So three of them must have linear relation between them. That linear relation gives relations like this. So its reasons are very simple. And what you are studying is an obvious object. Okay, so since I'm ran out of time, I'll just end with this. Here is a little ode to the heroine of our story, the modular group SL2Z. So mathematical developments are often led by her all-embracing majesty, it's said. This is the group JLN, according to Weil Herman, but the real story is SL2Z. Thank you. If people have some questions also, they can ask. Okay, even on the chat. Okay, notes. A few minutes maybe. Kari may be waiting.
Any questions from the participants?
Otherwise, you can write an email to me. Okay. I will always reply. Anybody can write an email to me, I'll reply. I'll send this file also to Dr. Uma. Shall I stop sharing now? Professor Adhikari is already waiting.
Hello, no problem. Please.
But anybody has a question,
How
please
are
let
you?
me know.
Thank you, sir, for readily accepting our invitation in spite of your busy schedule. Now I call upon Sri Bhargavi to propose vote of thanks.
Thank you, ma'am. Good afternoon, everyone. It is a great honor to propose vote of thanks to all who helped to make the session interesting. I thank Sir B. Suburi Garu for giving his valuable inputs on modular group and continuous fractions connected to the work of Maria Mirza Khani. It is my privilege to thank Professor G. Sudarshan Reddy Garu, Secretary cum Correspondent, for conducting the Faculty Development Program. I would like to express deep gratitude to our Principal, Dr. Achyuta Devi Ma'am, and our Vice Principal, Dr. Kavita Ma'am. And I also thank the staff and the students. Thank you, everyone.
Certificate download ಗೊತ್ತಾ ನನಗೆ ನಾವು ಪಟ್ಟಿದ್ದೇವೆ.
Sir, from our side, it's a small certificate of appreciation, sir. I just send you to your mail, sir.
Thank you. Thank you.
Thank you, sir.
I appreciate it.
Thank you, sir. Thank you very much.
So I'm all about waiting for Professor Adhikari's talk.
Okay, sir. Thank you. Good afternoon, sir. Good afternoon, Adhikari, sir.
Yes, hello.
Now I call upon P. Shweta to introduce Adhikari, sir.
Thank you, ma'am. Good afternoon to all. I, P. Shweta, lecturer, Department of Mathematics and Statistics, takes it as a privilege to introduce the resource person of this session to day one of 1 week National FDP organized by the Department of Mathematics and Statistics, RBVR Women's College. Sir Sukumar Das Adhikari is currently the Dean, School of Mathematical Sciences at Ramakrishna Mission Vivekananda Educational and Research Institute, Belur, Math, Howrah. His areas of specializations are number theory and combinatorics. Sir is the fellow of the National Academy of Science, India. Currently, he is the president of the Indian Mathematical Society. Sir received the M.K. Singhal Memorial Award for the year 2013 to 15 by the Indian Science Congress Association. Sir is the Distinguished Faculty Award of Homi Bhabha National Institute in 2015 and Doctor of Science Honoris Causa from Kazi Nazrul University, Asanul, West Bengal, India. Sir also given invited talks in many places, including one on analytical number theory held at Max Planck Institute, Bonn, Germany, in Megaku seminar at Nihon University, Tokyo, in the conference and in the workshop. Real-time release testing on Ramsey theory at University of Seville, Spain. Now I welcome Professor Sukumar Das Adhikari sir to take over the session.
Okay, first of all, I would like to thank the organizers for giving me the opportunity to speak here. Am I audible? Hello?
Yes, sir, you're audible.
Yeah. So my topics is some classical results in combinatorics and combinatorial number theory. So we talk about some early Ramsey-type theorems in combinatorics and combinatorial number theory, which include the theorem of Ramsey, the other results being those of Suhr and van der Waden, which share the credit of preceding the result of Ramsey in the class of Ramsey-type theorems. So I will explain that what is this preceding. So origins of some of the famous recent developments in mathematics can be traced back to these results. Now, the planning of the lecture is as follows. First, I shall give the general philosophy of the theme. Then I start from the beginning, the Pigeonhole Principle, of which the classical Ramsey theorem can be said to be a generalization. Now, some of these theorems, interrelations, and some generalizations will be discussed after that. So, general philosophy.
Are you sharing actually? Are you sharing?
Oh, I see, I see. No, I was telling, but there is some problem. Okay. Now it is okay.
Now it is okay. Now it is.
So sorry, I have to repeat it again because করবো এটা ওটা উঠছে না কেন? Okay, sorry, there was some problem in sharing my file. I went on telling few things. So once again, so I thank the organizers for the invitation. So the thing is, now it is shared, no? So we talk about some Ramsey-type theorems in combinatorics and combinatorial number theory, which include the theorem of Ramsey. And there are some earlier results we will be talking about, and which also fall in this scheme. And origins of some of the famous recent developments in mathematics can be traced back to these results, but we will be confining ourselves to very early results, which are rather combinatorial and not difficult to understand. So planning of this lecture is this general philosophy. Then we go to Pigeonhole Principle, some basic thing of which the Ramsey theorem is a generalization, and some theorems and interrelations and generalizations. So general philosophy of Ramsey theory can be said that regular substructures, the existence of regular substructures in general combinatorial structures, this is the phenomena which characterizes Ramsey theory. Now, most often what happens that there will be results that if a large structure is divided into finitely many parts, at least one of the parts will retain certain regularity properties of the original structure. We'll soon see, once we see some examples, it will be clear what I mean by regularity. And of course, another thing is that dividing into finitely many parts can be often said in colorful language. So a finite coloring is a finite partition. So suppose two coloring, red and blue, is just partition in two parts. So in some results in Ramsey theory, this large has to be defined. Okay, we'll come to that. So we'll be seen to have certain regularities. Now, this philosophy of this Ramsey theory can be put in a nutshell with the statement of Motzkin that complete disorder is impossible. Now the pigeonhole principle. What is pigeonhole principle? That I think everybody, all students know. The pigeonhole principle, if n plus 1 objects are put in n pigeonholes, then there will be a pigeonhole containing at least 2 objects. So this is a counting principle. If everything had not more than 1, then total would not be more than n. So this is just a counting argument. Similarly, this can be generalized. There are more general versions, but this will be enough for the time being. So if 2n plus 1 objects are put in n pigeonholes, by the same argument, there will be a pigeonhole containing at least 3 objects. Now the example. Okay, now here I'll stop to tell something. This Ramsey's theorem was proved by Ramsey for something. It was a lemma there. And after that was 1930. And after that, 5 years of that, this Erdos and Jacques, okay, there they rediscovered, okay, they needed some result which it was found that had been, let us Erdos found that it had been known 5 years back and it was proved. So this is again rediscovery of the result of Ramsey. But since Erdos goes around lecturing and asking questions and generalizing things, this subject developed. And then its name is the Ramsey theory. The subject grew up. And then with some hindsight, one could see that about 3-4 results of that, there was a result of Hilbert, which we may not discuss here. And there is a result of van der Waden, 1927. That was 3 years before this Ramsey's thing. And then there was 1916 result of Sur. This, with hindsight, you can see that the results fall in this category. And there is, I will show the link also, like when 1916 Sur's result was proved, that time Ramsey's theorem was not there. But today, after stating it, we will deduce it from Ramsey's theorem. So now before that, we are in the basic pigeonhole principle discussion now. So this Erdos-Jacques paper, where they proved Ramsey's theorem again, that also had history, and because of lack of time, I would not go into that. And that was a question, because there is women's, this thing we are celebrating, that Esther Klein, one girl asked this question, and then these people solved it. Okay, and I'll not go to that because of lack of time. Maybe if time is there, we can discuss at the end. So given a sequence of n square plus 1 distinct real numbers, so that if it doesn't contain a monotone increasing subsequence of length n plus 1, then it must contain a monotone decreasing subsequence of length n plus 1. So you cannot avoid a monotone sequence of length n plus 1 some way or other. Now, let us see the proof, because later on bigger things we cannot prove. So some few small things in the beginning. So given the sequence x1, x2, xn, a subsequence will be xi1, xi2, xin, where 1 is less than equal to i1 is less than i2 and less than equal to n. So this is the definition of subsequence. You cannot go back. So now, solution. So let us take a sequence of length n square plus 1. We take distinct real numbers to get a monotone increasing, strictly monotone increasing, strictly monotone decreasing, etc. Otherwise, we would have got monotone ordinary. So if possible, let there be neither a monotone increasing subsequence of length n plus 1, nor a monotone decreasing subsequence of length n plus 1. Now consider this function f from S to this z cross z. So xy, we are okay, and these integers, how do we define? Xi is the length of a monotone increasing subsequence of S, the largest possible length starting at ai, and yi is the length of monotone decreasing subsequence of S of largest possible length with its last term ai. So this example will clarify. So third element is 1 here. So that is A3. A3 is 1. Now the way it is arranged, one could have taken 1, 3, 4. That is the increasing sequence starting at increasing subsequence starting at 1, and that length will be 3. But we are looking for the largest possible. So then one can check that 1, 7, 8, 9, 21. So this is the largest. So its length is 5. So this first here xi means x3 in the corresponding would be 5. And what is this 1? Before that there is already this one can take, this is decreasing. So either you can take 2, 1 or 5, 1. So that is 2. So the largest possible monotonically decreasing sequence ending at 1 is 2. And largest possible length of the largest possible monotonically increasing sequence starting at 1 is 5. So this pair is 5, 2 for A3. So this clarifies this definition. Now, by the pigeonhole principle, because you see, they go, there is no n plus 1 monotone, this thing, so that these values will not be more than n. And this length will be, any question? So length will be between 1 and n. So that will be n square. On the right hand side, the size is n square, and we have the sequence is n square plus 1 element. So there will be ai and aj with I less than j, such that fi is equal to fai is equal to faj. That is, fai is xiyi and faj is xjyj. So out of these two, one is less. So let ai be less than aj. Then considering a monotone increasing subsequence of length xj starting at aj, which is by definition that is there. And now if we add the term ai, which is smaller than this in the beginning, so from ai we get a monotone increasing subsequence of length this starting at ai. So that is a contradiction, that how can this to be that xi is supposed to be xj. So similarly, therefore xi is greater than xj because of this, and which contradicts equation 1 that xi equal to xj. Similarly, if ai is greater than aj, then considering a monotone decreasing subsequence of length yi ending at ai, if we add the term aj at the end, we get a monotone decreasing subsequence of length yi plus 1 ending at aj, and same contradiction will now prove that that is not possible. So there is either a monotone increasing sequence of length n plus 1 or a decreasing one subsequence of length n plus 1. Now we go to an well-known example, which is can be said a prelude to Ramsey's theorem, and some seeing this pigeonhole principle clearly. So if you have a party, this is a very well-known in the school question. If you have a party of at least 6 people, you can guarantee that there will be a group of 3 people who all know each other, or a group of 3 people all do not know each other. So this proof is by graph. So what we do, from A is 1, every person is depicted by a point here. So we join A with other 5, and if we join, if A knows C, okay, so we join by red, and if they doesn't know, then we join by blue. Now see that there are 5 lines joining A to B, C, D, E, and F respectively. So out of 5 points by the pigeonhole principle, here it is very easy to see that at least one of them has to be 3. Because if both are less than or equal to 2, then 5 cannot be there. So either 3 red or 3 blue. So without loss of generality, let 3 red, A to C, A to D, and A to F. Now, if CD had been red, then we get a red triangle. So that would say that A knows C, C knows D, D knows A, and would be true. So we have to assume that CD is blue. Similarly, when you consider the edges AC, AF, then by the same argument, CF has to be blue. And similarly, considering AD and AF, that DF has to be blue. So now we are trying to avoid a red triangle. We ended up in getting a blue triangle, which is CDF. So either way, either three people, all of who know each other, or three people, none of them know each other. So that is proved now. So there is some generalization. This is Ramsey's theorem, that if you take K, R, and L, positive integers, and to avoid trivial cases, let L is greater than or equal to K, then there exists a positive integer N depending on K, R, and L, such that any R coloring as I told, the partition into R disjoint subsets. So any R coloring of the K subsets, we are coloring the collection of K subsets, K element subsets of N. There in the previous argument, we were two people, whether two people know each other or they don't know each other. So our K was 2 and this R was also 2. They know each other or they don't know each other. So red and blue. We get it. So here it is generalized. So you R coloring of the K subsets of the set, the square bracket N. This square bracket N is the set 1, 2, 3 up to N. Then there is this could be any set of N elements, but it is easier to see with the set 1, 2, 3 up to N. So there is an L subset, all of whose K subsets are of the same color. So L subset meaning we are considering K subsets of 1 to R, 1 to N, but there will be L subset which can be some C1, C2, C, okay, CL, and all of whose K subsets are of the same color. So this is the statement. We will not go to the proof of this because that there is not enough time for that. Only thing I want to show that this 1916 result, though Ramsey's theorem is 1930, this proof was by Sur was by different method, of course. And now we saw that this Ramsey's theorem trivially implies this. What is the statement of Sur's theorem? It says that for any R coloring of the set of positive integers, there exists a monochromatic subset XYZ of that, such that X plus Y equal to Z. Okay. So this is what, that if you have partition of positive integers into R parts, okay, then there is a, in one part, you will find X, Y, and Z such that sum of the two is the other one. The situation is described by saying that the equation this has a monochromatic solution because in one part is one color. So you get a X, Y, and Z from the same part. So it is said that monochromatic solution. Now deduction of Sur's theorem from Ramsey's theorem. So we take this, as I told, that K in place of K we put 2 and we want a triangle, so put 3. So where NKRL is as defined in Ramsey's theorem. Now we give R coloring, any R coloring from the set of positive integers 1 to N to 1 to R, this is the color. So that induces an R coloring of the, because to use Ramsey's theorem, we have to get coloring on 2 element sets. So on IJ, this pair, we give the color of the distance between I and J, because our color was defined on integers. So this pair, this 2 element sets, this tuple, chi star on this tuple is chi of this distance. When it is a 2 element set, means I is not equal to J. By definition, there exists a 3 element subset with A less than B less than C, such that this, all these tuples, 3 possible tuples from the 3 element set, they have the same chi star. But what is chi star? This is nothing but chi of B minus A, chi of C minus B, and chi of C minus A. But this is already trivial to see that B minus A plus C minus B is C minus A. So if you take this as X and this as Y and this as Z, then we get a monochromatic solution of the equation X plus Y equal to Z. So now we come to Van der Waals theorem. So rightly finding is there was a book by Kinchin, okay, that three pulse in number theory. So there one of the pulse is Van der Waals theorem. So the theorem of Van der Waals we are going to state now. It led to many interesting developments in combinatorics and number theory. And we may not be able to go into those things now, but I think I shall try to mention few things at the end. So observation, let us take this and color by two colors. So 1, 4, 5, 6, and then again 11, 12, 13, 14, 15. So 1 is put red and next two elements are put black. Then next 3 are red, next 4 are black. This way, so this way we can see that there is no monochromatic infinite arithmetic progression. Because if we consider about red colors, then there is bigger and bigger holes in the red colors by these black colors. Because the length of this successive sequence of consecutive black elements is increasing. So is this for the red. So you can never get an infinite arithmetic progression. Whatever common difference you take, there will be in the other color, there will be more than that consecutive elements. So you cannot have an infinite arithmetic progression of any either black or red. But then by doing this, that you can try in other ways also, we could see that here is a 3-element arithmetic progression of red. Here is an 5-element. So as you create more and more, you get consecutive block of, in this process, there can be other ways of coloring also, but in this process, so then now is it true that may not be infinite, but arbitrarily long? So that was the question. So this was, I think, Boudet, it was in Van der Waals theorem, it's a Boudet's conjecture. So, and it is also known that now that Sur also conjectured this. So this was, we can let us assume that it was conjectured by Sur and Boudet independently, that given k are positive integers, there exists this is called Van der Waals number. This is a positive integer such that for any R coloring of this length, 1, 2, up to this, if you go, there is a monochromatic arithmetic progression of k terms. Okay. So if these are colored R colors, that means this is partitioned into R parts. Then in one part, there will be an arithmetic progression of length k. So that is Van der Waals theorem. And now this we go for, we will not go to the proof or any other, we can say a few more general forms of that later on. So now higher dimension and generalization of Sur's theorem. So Sur's theorem, for any finite coloring, we said, we observed that in the Sur's theorem says that there is monochromatic solution of this equation in 3 variables. Now again, if you take Van der Waals theorem and stick to the particular case of length 3 arithmetic progression, then you get x, y, z satisfying this. X plus z is equal to 2y, and the arithmetic progression x, y, z will satisfy this. So we get two equations, x plus y equal to z, x plus z equal to 2y. Now let us ask the general question. Given an, so Rado was a student of Sur, and so he took care of this problem. So given an equation with integer coefficients in n variables, if their Ci is not 0, because then the number of variables will go down. Okay, so it has a monochromatic solution where xi may not be distinct in Z plus with respect to any finite coloring if and only if some of the some non-empty subset of the coefficients sum to 0. So let us go back to the equations we wrote in the last. X plus y equal to z, bring them to this side, right, in this form. So x plus y equal minus z equal to 0. The other one becomes x plus z minus 2y equal to 0. But in the first one, you take the coefficient of y is 1, coefficient of z is minus 1, sum is 0. And here coefficient of x plus coefficient of z is 2 and coefficient of y is minus 2, sum is 0. So here this theorem says that this is not just particular this thing. So if this equation c1 x1 cn xn equal to 0, if this has to have a, this is called regular then, monochromatic solution for any finite coloring, then sum of the coefficients should sum up to 0. So as we see in these two particular cases, in first one, 2 coefficients sum up to 0, in the other one, all the 3 coefficients sum up to 0. Now, here one thing I should say, that if sum of the, none of these sums 0, then there will be, consider all the sums and take a prime which doesn't divide any of this, because then there are finitely many, none of them 0. So there is a prime which doesn't divide any of those sums. Then there is something called SP, I didn't write this in my type thing, SP mod coloring, which is what, when you take integer, a rational numbers even, and C by D, and take that particular prime out, whether from above or below, so that the remaining now numerator and denominator are free from P, then that can be considered an element of the finite field FP, a non-zero element. So this is a P minus 1 coloring, and one can show, it is not difficult, but I will not do this here, that if none of the coefficients sum up to 0, none of these subset of these coefficients sum up to 0, non-empty, then that P mod, that a prime P which doesn't divide any of these sums, and then take SP mod coloring, but in that one can, that will abstract. So if some color can abstract, then SP mod color can abstract. But one thing one should observe, if the coefficients change, one can change the coefficient Ci, suppose C1 you take factorial K. Then what happens is that prime value goes up and the number of coloring goes up. So there was a conjecture of Reddy, still open, which says that if some equation in n variable is not regular, then there is some value already, okay, some fixed integer depending on n, okay, call it Rn, such that there will be some Rn coloring for which there is no monochromatic solution. So this is Reddy's conjecture, and it has been solved by Fox and Clydeman in the 3 variable case. 3 variable case, 24 coloring is there, such which obstructs. Okay, any 3 variable, if it is not regular, then there is a 24 coloring can be given for which, but that 24 is still not known to be optimal. One may have can improve 24. So that is, so I told this open question because people, a subject really lives on open question. So now Folkman's theorem. So this is another type of, there also another thing I didn't mention, this Reddy I get the right abridged version. The general version is a system of linear, homogeneous linear equations. So there is some column condition which I will not go into. Now Folkman's theorem. So given any 2 positive integers, there is a positive integer n such that if square bracket n is are colored, as I told, where square bracket n is 1 to 3 up to n, then there are positive integers k positive, okay, and satisfying that total sum also. That means all the partial sums will be less than n, such that the elements, all finite sums, are identically colored as I varies over different non-empty subsets. So you see that earlier, so this is another generalization, okay, of Schur's theorem is what? X, Y, Z. So there is 3 element set, and whatever X and whatever Y, and same is X plus Y. So there is 2 element set, X, Y, and X plus Y. So here it is increased to K elements. All partial sums are of the same color. So this is Folkman's theorem. There is another generalization further, because you can have an infinite sequence, all of whose finite sums are of the same color for any. So we will not go into that. So now we say some generalizations of van der Waals. One is Grunwald's theorem. It is a higher dimensional. One can say that this is a higher dimensional generalization. So D and R are positive integers. So any finite set, if you take from that, this can be said in lattice points in D-dimensional RD, and any small r coloring of Z plus D, there exists a positive integer A, and I'll show there is a figure there, otherwise it is difficult to understand. And a point V, that is a vector, such that this A into S, that is a homothety. So things will expand, and V is shifted. So that means this is a translated homothety. Multiplying by A, so structure will look same, but only thing they will expand, and V is shifting. So now note that when D equal to 1, we are in 1 dimension Z, then put S, the consecutive K integers, then a translated homothety like this is nothing but an arithmetic equation. So this generalizes to higher dimension that one can see. Now let us take this thing. This thing is not visible because the points are this here, 3 points and 2 points. And so the translated homothety is that you shift and that will look like this. So it has the same sort of points in the beginning, and then it expanded and shifted. So the same 5 points, okay? So this is translated homothety. Now there is another theorem. This is Hell's-Dewey theorem. So for that some terminology will be needed. So CTN is, these are words, x1, x2, xn is the words of length n, and xi belongs to this alphabet. Alphabet, like when in English, we write DOOR, this is a word, and the letters are coming from this English alphabet. So here the alphabet is so that we can decrease, increase everything. There is no bound here, because so this xi belongs to 1 to t, the alphabet, and your word length is n. So this is the notation CTN. Now a combinatorial line in CTN is a set of t points, okay, that has this alphabet. In CTN, ordered as x1, x2, xt, where you write like this for j belonging to a non-empty subset. This I think if I show, that will be easier. Some non-empty subset of the index thing, this will be same. Any xj will be s for all, it will not change. And the other one, so for some cj, it will be, and here it will be all s. x1j is equal to 1, x2j equal to 2. So that is running coordinate. So at least one running coordinate, and there are some this sort of fixed coordinate. Now let me show this thing because that will become vague. Like this. This is a 5-letter, 5-letter, 5-letter. 1, 2, 1, 2, 3, 2, 2, 2, 2, 3, 3, 2, 3, 2, 3. So now you see that there is in the first place, it is going 1, 2, 3. In the third place also it is going 1, 2, 3. And other places are fixed. 2, 2, 2, 2, 2, 2, 3, 3, 3. So that's what we are telling. But what may happen, there may not be any fixed place like 3, 3, 3. But there must be one, at least one, where it will go running. That is called running coordinate. 1, 2, 3. So in here it is the two such things are there. In the first coordinate and the third coordinate. So what we mentioned here, that non-empty subset of the index set such that xsj is equal to x. When the first x1, then this is 1. x2, then that thing is 2. Like that. It is running coordinate. And the other one, the remaining thing, it may be no remaining, but that will be fixed. Now, Helmholtz theorem now says that giving any two positive integers r and t, there exists some n, which depending on, there is a Helmholtz function of on two variable rt, such that if Ctn is r colored, so this is r, depending on the number of colors, okay? So, and this r and t has been given, okay? So, coloring by r and t is like the alphabet length. So, this Ctn is r colored, then there exists a monochromatic combinatorial line. So, now let us see that what does it mean? For t equal to 3 and n equal to 5, the following example, which I already described, that this is in C35, there is a line, okay, C35 is so line length will be 3 only, because 1, 2, 3. So we see that collection of the words in C35 are in 1-1 correspondence in the obvious way to the subset of the integers up to 3, 3, 3, 3, 3, because your maximum is 3. So the largest number can be here is 3, 3, 3, 3, 3, 5 3. Okay. So this 1-to-1 correspondence, of course, this 1, 0, 0 is not there. The minimum is 1, 1, 1, 1, 1. So this is a subset of this, where the integers have their usual expression in decimal system. Thus, the three words in the above combinatorial line correspond to an arithmetic progression with common difference 1, 0, 1, 0, 0. Because first coordinate and third coordinate, they are moving coordinates. So the common difference is 1, 0, 1, 0, 0. So, but then for general thing, you just t you increase, okay, and base t you will do, and then things will become again arbitrary length arithmetic progressions can be. So this the theorem of Helmholtz, now revealing the the way Van der Waals theorem was stated, it was like properly number theoretic result. But then Helmholtz, there is not much. It is a just set theoretic something. So this is a combinatorial result. So this as this it was said by Graham, Rothschild, and Spencer. So the Helmholtz theorem strips Van der Waals theorem of its unessential elements and reveals the heart of Ramsey theory, probable combinatorial. Okay. So perhaps, okay, so I tried to explain in my way the theorem of Helmholtz revealing the combinatorial nature of Van der Waals theorem would claim that this pearl of number theory belongs to the ancient source of combinatorics. So, and this is the statement of Graham, Rothschild, and Spencer. I think I have some time, so I'll say some application which I have not typed. There are many applications of Van der Waals theorem in mathematics. One itself, I mean, it was a conjecture of Gurevich. It says that color the plane R2 in finitely many colors. So these finitely many colors can be very complicated. Suppose you make rational, irrational, irrational, rational, rational, rational. So with coordinates, rational, irrational, irrational, rational, like that, 4 coloring. Then on the top of that, if you go alternate segments, either concentric circle or these parallel lines, okay, x equal to 1, x equal to 2, x equal to 3, alternately you change color. So this way you can soon get more colors multiplying on that. So then things become very complicated. You don't know which color is where. So if I give 200 colorings, then it can be very complicated. Now, what is the conjecture of Gurovich? As long as the number of colors is finite, give any delta, there will be a triangle of area delta whose 3 vertices receive the same color. Okay. And this was very complicated proof by Graham was there. And when I was writing somewhere, then I tried to simplify, and somehow luckily I could simplify it to 1.5 page, something with some inductive argument. But the main idea is Graham's idea, that is using van der Waals result. And then the conjecture is that, now question, whether it can be done for a parallelogram, that given any delta and any finite coloring on the plane, there is a parallelogram of area delta, all of those 4 vertices are receive the same color. And this is not settled either way. But with Yang-Gao chain, I could prove that one can do for trapezium. You get 2 sides parallel of the quadrilateral. So there is trapezium whose area is delta and 4 vertices are of the same color. But that becomes a bit complicated coloring. And the question is still open, that what about this parallelogram? We don't know. So this is, on the other hand, van der Waals theorem was a prelude to a theme which essentially belongs to the realm of number theory. So the development, so there is a conjecture that there is a big difference between the source theorem and van der Waals theorem. These 2 theorems we discussed in the beginning. Whereas source theorem is not a density result, because if we take the odd integers, which are half of the integers are odd. So if you go density, natural density is 1, but then there is no monochromatic solution. There cannot be 2 odd if you, whose sum is odd. So then sum will become even. So there is no monochromatic solution in this coloring of, in the set of all, there is no solution in the set of odd integers of the equation x plus y equal to z. On the other hand, for van der Waals theorem, it was observed, that was Erdos-Turan conjecture, that here things are a bit different, quite different, as far as this point is concerned, because here it is not, it is just a density result. So suppose when you take partition into R part, then at least one part have natural density. What is natural density? Take the number of elements in your given set, subset of positive integers, up to k, be nk, and then divide by k and take the lim sup. So as you see that the odd integer or even integer, number of even integers up to 100 is 50 by 100. Similarly, go on increasing, so it is half. So if it is colored in R colors or R partition into R parts, then at least one part will have then natural upper natural density 1 by R. So the conjecture is that if that, now it is a theorem, I'll say that if the take a subset of positive integers whose upper natural density is positive, then it must have arithmetic progressions of arbitrary length. And it was proved by Reddy first by combinatorial method. and later Furstenberg did it in ergodic method. And there are many, now there is a subject called ergodic Ramsey theory, where Bergelson and many other people have contributed a lot, and that subject is growing. And then there is another conjecture that if take integers a1 less than a2 less than a3, so subset of positive integers a1, a2, a3, if these reciprocals, sum of the reciprocals, so 1 by a1 plus 1 by a2 plus 1 by a3, if this sum diverges, then also it should have arithmetic progressions of arbitrary length. And this is no, people do not know which way it is true. This is Erdos conjecture. It will be very difficult. But the particular case of this, which is primes, okay, that is Green-Tau theorem, famous Green-Tau theorem, that we know that these reciprocals of sum of the reciprocals of the prime, that it diverges, and that this but of course one can get some similar sequences like that, but the general that if the reciprocal sum of the reciprocal diverges, that is still beyond our grasp. Even this itself already becomes very, very difficult. So thank you. I'll stop here. If any. Hello.
Thank you, sir.
Am I audible?
Yes, yes.
Sir, thank you, sir.
So I'm through now. So somehow I didn't type many pages. I thought of going slow, but some places I didn't go so slow, I think.
You can mention your book, which is also very nice on the subject.
Yeah, I have to revise that book. You see, when I wrote that book, then it was in 2002. Then I gave back that example of 26 primes, which are in arithmetic progression. That time that was by computer search it was found. But now, of course, this Green-Tau theorem is there. So I should mention this. It is not, I have to update this book. Okay, there are many other results which have been proved or improved. Many questions, I mean, are answered. So I have to rewrite, have a second edition of that volume, not getting time, maybe next year. So that was actually Ramsey theory book. And some Ramsey theoretic results mainly are there, but there are some other results also at the Giro sums and things like Giro sum also is some sort of Ramsey theory that you cannot avoid. Okay, like if you take some k integers, then there is some of those integers will sum up to a multiple of k. So that's what in children book it will be there, that if one take 10 integers, then there will be some integers, so either 1 or 2 or 3, their sum is multiple of 10. Okay, and then the way to see is that write down that first a1, then you write a1 plus a2, then a1 plus a2 plus a3, then last finally a1 plus a2 up to a10. Now, if none of them is 0, then all of them belong to the set 1 to up to 9 mod 10. So 2 of them are by Pigeonhole Principle congruent to each other mod 10, and then their difference is 0 mod 10. So not only that you find some non-empty subsequence whose sum is multiple of 10, we get that these whichever way you arrange them, there will be some consecutive ones whose sum is a multiple of 10. And same thing can be generalized to n, and which you can consider things elements in Z mod nz. But then there is a generalization. This is a Davenport constant. In Professor Suri also has worked in this. So in any finite abelian group, you can ask this question. But there are things results in non-abelian case also. So this is also one Ramsey type, one can say. Okay. So I'll rewrite this Ramsey theory book.
Thank you, sir, for readily accepting our invite in spite of your busy schedule and for enlightening us by your lecture, sir. Now I call upon P. Shweta to propose formal vote of thanks.
Good afternoon, sir. On behalf of organizing team and its privilege to propose a vote of thanks on this FDP. My humble thanks to Sir Professor Sukumar Das Adhikari, sir, for delivering this lecture in our department. Sir has given an excellent explanation on Pigeonhole Principle, Waals Theorem, Rado's Theorem, Ramsey's Theorem, Folkman's Theorem, and Hales-Jewett Theorem, which will be very helpful for us. I also thankful to Achita Devi ma'am, Principal of RBVRR Women's College, and Shweta Srivastava ma'am, HOD of Maths and Stats, for conducting the faculty development programs. Thank you, sir.
Sir, will you stop sharing this so that I can share the appreciation certificate, sir?
Thank you. Sure, my file was till the end was not shared or something.
Sir, will you please stop sharing this so that I can share the certificate?
You have to stop sharing.
Oh, at some point. There was some problem. In the beginning, it didn't share. Again, I corrected it. And then again, it stopped. Is it?
Sir, you have to stop sharing this, sir.
It is visible now, but you can stop sharing now, I think.
Okay, okay. Thank you. Okay, there is no lecture, I think, now.
Sir, would you please stop sharing this so that I can share you the appreciation certificate, sir?
Okay, I don't know how to, I have to call somebody.
Somewhere it will say stop sharing some near the.
I'll call someone.
Or you could remove him as co-host, then it automatically will go. I think.
Yes, sir.
Yeah, yeah. But I am calling my computer person because it's sharing টা বন্ধ করতে হবে কি করে? No. Oh, yeah. Okay, okay. I could not find it. Okay. Now it is done.
Yes, sir. Thank you, sir.
Yeah, it was somewhere I could not see.
Please accept our certificate of appreciation, sir.
Thank you.
Sir, I just mailed the certificate to your mail ID, sir. Thank you very much, sir, for readily accepting our invite.
Okay, okay.
Thank you, sir.
Okay, thanks a lot. No lecture today, no?
Yes, sir. This 2 sessions only we have, sir. Dear participants, again we will be rejoining tomorrow at 3 o'clock for the next session. Thank you one and all for patiently listening.